So welcome, my name is Petra Deakins, and as President-elect of the Paleoceanography and Paleoclimatology, it's my pleasure to welcome you to the 19th Annual Emiliani Lecture. I want to start by just taking a moment to thank those of you that took the time to nominate your colleagues, and also the people that served on the election committee for selecting this year's speaker. Before we start, I just want to say a quick word about the AGU Centennial. You may have seen some stuff about this around the meeting so far, but beginning in the fall meeting of 2018, AGU will start its celebration of advancing Earth and space sciences, and that celebration will start at the meeting in DC and culminate with a celebration in the fall meeting of 2019 in San Francisco. And one of the ways they're looking to promote that history is through collaboration with Storycorps and developing an oral history. So we know that many of you have fantastic stories about scientific developments and about people, about scientists, about your colleagues. So if you have ideas of stories that you think ought to be told, please feel free to email me or Fegan, but you can also just directly go to the Centennial website of AGU. So at this point, it's customary to give you a little bit of background about why this named lecture was named after Cesare Emiliani. Emiliani was born in 1922, where he received his first PhD in 1945 in micropaleontology. Shortly after that, he went to Chicago, where he worked with Harold Urey, and it was during that time that he and Urey developed the techniques to measure the isotopic composition of foraminifera. Most importantly, it was during that time that Emiliani realized that the geochemistry of foraminifera could be used as tape recorders and record changes in oceanographic conditions because they were recording the chemistry or the conditions of the water in which the calcite was precipitated. Emiliani completed his second PhD, this time in geology, in 1955, and then he moved to Miami's Institute of Marine Sciences, which later became the Rosenthal Institute of Marine and Atmospheric Sciences. In 1967, he established the Department of Geological Sciences there, which he chaired from its inception until his retirement in 1993. He was also a key proponent of the JOIDES program, which is the foundation of the drilling program that carries on today as the IODP and is so important to many of us in our work. Of course, Emiliani is best known for his measurements of foraminifera oxygen isotopes and for establishing that the ice ages were cyclical and providing strong evidence in support of Milankovitch theory, which essentially revolutionized the ideas about history of the oceans and climate. But it's also well established that I had a pretty good sense of humor, which is probably required if you're going to be the chair of the department for over 25 years, so that makes sense. And I was reminded recently of a story that I think a lot of you are familiar with, but I think is worth telling again. In 1984, Emiliani received a proposal from the National Science Foundation and was asked to review it, and that proposal was written by Cesare Emiliani. And Maureen Ramo actually tweeted this out, which is an actual scanned copy of the review. And it's got some real gems in it, which I'm going to share a couple of them with you. I knew Emiliani is a genius. He told me so himself several times. But I did not know he was a genius of such transcendental proportions. It's full of these kinds of tidbits. By the end, he even managed to ask for double the funding. But among all the humor is actually another statement that I think is actually really essential to many of our careers, and that is this one. Is there any question in anybody's mind that the last deglaciation is important? Is it not the key to the evolution of our modern environment? So Emiliani is the father of paleoceanography, not for one data point and not for one record, because he recognized that the importance of developing records of past climate change in order to better understand our modern climate and our future climate. And that brings us to today's Emiliani speaker, because Thomas Stocker has built his entire career on using lessons from the past climate to inform predictions of future climate. So it's my pleasure to say that Dr. Stocker is our Emiliani lecturer today. He is a professor of climate and environmental physics at the University of Bern. He was elected to be a fellow of AGU in 2012 and has earned many other awards, which I will not take the time to list, otherwise the introduction will go on too long. His research has focused on climate and paleoclimate modeling, and he's noted in particular for his pioneering efforts in the development and use of intermediate complexity models that include biogeochemical processes. He's developed ideas about ocean heat transport and the role of thermohaline circulation in global and regional climate, as well as ocean and atmospheric biogeochemistry related to the carbon cycle and ice core science. In addition to his impressive record of his own research, Dr. Stocker has been a key contributor to the Intergovernmental Panel on Climate Change. This included being the lead author of the technical summary of the third assessment report, being a coordinating lead author in the chapter of global climate projections in the fourth assessment report, and then finally being the co-chair of the entire working group 1 for the fifth assessment report, which came out in 2013. But after spending 17 years contributing to the IPCC, Dr. Stocker is now returning back to the foundation of his career and coming back to paleoclimate modeling. And today he's going to give us a brief history of the co-development of proxies and models in improving our understanding of climate change.
One second while we honor Dr. Stocker with his award. Please applaud. This is your mouse.
All right, thank you very much for this very kind introduction. Good morning, everybody. It's a great honor and pleasure to speak to you this morning and to be selected as the Emiliani lecturer of this year. Never dreamt that that would happen at some stage. Unfortunately, I have never met and interacted with Cesare Emiliani, although chronologically it would have been possible, but it's as usual with these things, you only realize after the facts that you've missed important meetings and encounters. What I want to do in the next 40 minutes or so is to give you a flavor with a historical path also of the interaction between the development of models, and not only very high resolution models, but also a hierarchy of models, and the upcoming and emerging interesting proxy data from various paleoclimatic archives. And as you can imagine, I will certainly focus on polar ice cores because they have certainly, for me, been extremely stimulating in various aspects, not only by the time resolution of these records, but by the sheer amount of data and the globality of the data that has come from these paleoclimatic archives. I have thought hard about finding a connection with Cesare Emiliani, and there is an indirect one. Cesare Emiliani actually had something to do with a former director of the institute I'm working in at the University of Bern, and that's a colleague, Johannes Geiss, who is a space physicist. And all the people who were actually exiting this room just before our lecture here, they know Johannes Geiss very well. Well, Johannes Geiss is a space physicist who actually deployed the very first physical experiment on the moon. Of course, Buzz Aldrin had to do that in 1969. He unrolled the solar sail that you see here in this picture on the right side. And lo and behold, these two eminent scientists, Cesare Emiliani and Johannes Geiss, they published a paper together in 1959, incidentally the year I was born, so I could know about this, on glaciation and their causes. Very interesting that the space physicist was thinking about glaciations, and see what they wrote in the abstract. While smaller glaciations may have been largely or entirely patterned by the astronomical cause or causes, terrestrial factors had an important effect in determining the course of the larger glaciations. I've highlighted this sentence in the abstract because it indicates that there are different types of glaciations, large ones and smaller ones. And it turns out, as you will see at the end of this lecture, that this is a question that is still open and that we would like to address in one of the forthcoming projects. If you go further in the text, you see that they talk about the difficulty of assessing the timescales of Pleistocene events. They also say this difficulty arises from mainly the inherently discontinuous and fragmentary character of the continental record. Well, if we remember 1959, there were no ice cores among the classical methods that they quote. And also, paleoclimate modeling has not yet been invented to speak of. That was a very different time from today. Now we have polar ice cores, we also have paleoclimate modeling. But at that time, science already provided very important information that could have been climatically relevant, and a few people actually recognized that. I love this picture because it is dynamically based. It's a classical paper by Henry Stommel, published in 1958, so 1 year before Emiliani and Geiss published their paper in the Geologische Rundschau. And it shows the deep circulation in its dynamically consistent framework. You see a large current flowing from the North Atlantic, from the sources of deep water formation, down all the way to the Southern Ocean, where it joins the deep circulation around Antarctica, flows into the other basins. Of course, we know the circulation has a climatic role, and it has been advertised quite a lot in the past 40 years. But that is sort of the first dynamical depiction of it. Moving now to the data that came out a few years later from our institute at the University of Bern. My dear colleague and predecessor Hans Oeschger and his colleagues analyzed the isotopic composition of the carbonate sediments in Lake Gärzen Sea, close to Bern, and they found these variations here, radiocarbon dated at around 12,000 before the present, and in a typical and then mechanical cut and paste exercise, indeed with scissors and glue, they pasted a curve next to this graph from Gärtzensee from Greenland, a curve that was measured by Willy Dansgaard. You see here on the right side, looking at polar ice cores in great astonishment. And you see the section from a depth of about 1,800 meters from this Die 3 ice core. Cut and paste is an exercise that created new knowledge here. As you see, this correspondence between a climate signal in Greenland and a climate signal somewhere in Central Europe is very inspiring. Essentially, the same wiggles can be identified down to a centennial timescale. That's indeed a remarkable discovery. Let me go now back to the model in this ping-pong back and forth, and I've indicated that in my top bars, if you haven't noticed yet. Wherever the models are involved, it's red. Wherever the data are involved, it's blue. Around the same time, this very inspiring paper by Wally Broker and colleagues suggested that there are two stable modes of circulation in the world ocean with climatic implications. And it was not before long that a PhD student at GFDL actually simulated that using what you would call today a very a simple and coarse resolution ocean model consisting of just one basin crossing the hemisphere. And you see here the meridional overturning circulations that he could realize in this model, in this dynamical model, already back in 1986. This paper was extremely inspiring because it showed that the ocean could have all combinations of deep water formation, both in the southern and in the northern high latitudes, and the cross-equatorial flow that you see also in the two panels. Of course, this is associated with very different meridional heat fluxes, which, as it was suggested then, would actually influence the surface climate in the respective hemispheres. We're going back to Stommel again in 1961. These were all the initial threads that were ready to be picked up by the community, but at that time there was a sort of a silo thinking where the theoreticians or the modelers would not look or converse with those people who go out to sea or to the ice and collect the data. You see here two stable equilibria in a diagram of salinity and temperature resulting from a very simple but inspiring box model published in 1961, then rendered in a PhD thesis by Joachim Marotzke in 89, and we used a model of intermediate complexity, a 2.5-dimensional ocean circulation model to show a hysteretic behavior, which gives rise to interesting suppositions about the importance of freshwater fluxes and their changes in the climate system. But it's really only the data that moves us forward here. The data in particular from the ice sheets from Greenland and Antarctica, as you see here in this graph that was published in 1998 by Thomas Blunier, who for the first time synchronized across the entire planet two paleoclimatic records based on the methane concentrations that were measured in all three ice cores. You can see here essentially 50,000 before present into the deglaciation. We remember Emiliani's statement about deglaciation. Who could not be interested in that? But before deglaciation, there are also interesting wiggles and changes, abrupt changes, the so-called Dansgaard-Oeschger events. The synchronization actually showed that some of the large events, which are noted here, A1 and A2, kind of occur during a similar time as some of the big Dansgaard-Oeschger events. In fact, only 2 years later, Nick Shackleton, who's also was an Emiliani lecturer, among all the other important things that Nick left us through his science, found an extremely interesting sediment core on the Iberian margin. And in this graph of his article in Paleoceanography in the year 2000, he argued that he actually sees both Greenland and Antarctica in one single sediment core. It's quite interesting to compare the ice core slide that I showed before to this slide here before we had to do the synchronization via the greenhouse gas concentrations. Here you do the synchronization via the careful selection and the lucky selection of one single sediment core that samples both water masses and their variations at the benthic from the Antarctic and in the planktic in the upper layers from Greenland. You can see this corresponding dynamics here very well. Now this core and these data have inspired Sigfús Jonsson, who I also want to remember in this lecture, an ice core scientist from Iceland and Denmark as well, who has had a great career initiated in mass spectrometry, but then essentially being involved in all big ice sheet drillings and their interpretations of the past 40 years. He once visited Bern, and this is a little anecdote I want to share with you. Looking at this synchronization of Thomas Blunier in 1998, Sigfús immediately started thinking, and when he came to Bern, he over a fondue, I think it was, he said, well, Antarctica looks like the integral of Greenland, but I don't know why. Well, at the same time, we were thinking from a modeling point of view, what could be the reason for that observation? And I spontaneously said, well, I think we've got an idea, and that's how we came up with this thermal bipolar seesaw, an extremely simple, probably the most the most simple climate model that you can think of. It's essentially an exercise to try to explain and remove the confusion between leads and lags, or synchronicity or asynchronicity between ice core records from Greenland and Antarctica. And the idea here is that there must be somehow an integrating heat reservoir. At the time we thought it may be the Southern Ocean, but that stimulated many other papers that disagree with that. And I think it's very satisfying to see that models are actually exploring that early hypothesis of the bipolar seesaw. But the bipolar seesaw really got its confirmation as a concept, and as a concept also with predictive quality, the predictive quality being that these Antarctic isotope maxima should actually occur with every Donsker-Dushker event. In the original synchronization, it was only seen out of the noise in these ice cores at a few of the large Donsker-Dushker events. But it was the deep ice core from Dronning-Maudland with the then unprecedented resolution that allowed us to synchronize to the extent that each Donsker-Dushker event was seen with a counterpart in Antarctica. A real proof of that was the correlation, the remarkable correlation across the hemispheres of the duration of the northern stadial, which is depicted here in the horizontal, and the amplitude of warming out of the isotope record in Antarctica. And you can see here, during the last ice age, each of these Donsker-Dushker events that were at that time analyzed in 2006 essentially lied on a straight line here to a good approximation. Isn't that remarkable? Across the hemisphere, this correlation that seemed to be linear. A further analysis a couple of years later then showed that there is a twist to that. For some of the Donsker-Dushker events, there is like a saturation here in where the warming is not really taking pace with the duration of the cold event in the northern hemisphere. But essentially the linear relationship here holds. Now playing back the ball to the models again, of course the colleagues were stimulated and intrigued by the simplicity of this model. You could actually fairly say this was an inadequate model, but it started a thinking process. And I think even the complex models should today start thinking processes rather than making categorical statements. One of the thinking process concerns the question, where is this heat reservoir? And in this simulation, which is by itself interesting because it's a self-sustained oscillation in that climate model that Vettoretti and Dick Peltier were using at the University of Toronto, you see these large fluctuations in temperature caused by switches in the meridional overturning circulation. Again, no freshwater flux perturbation, but simple self-sustained oscillations. In such a configuration, you see in the lower graph, the heat reservoir that is absorbing heat and giving off heat to the climate system in the tropics, essentially. That's a surprise and a very important result, at least applicable to this model, where you see that for each of these cycles there is, in fact, heat reservoirs of substantial size in the tropics, but also in the high latitudes, as you see by these alternating colors of yellow and blue over the course of the simulation of about 3,000 years. But is that the end of the story? Not really. That has stimulated another study with a different model, obviously. And these authors here recently came to the conclusion, well, it's, the heat source is around Antarctica. Now, there is very compelling analysis of this study, but we're not really clear where this heat source now really is. And therefore, the modeling will go on to explore the dynamics of this bipolar seesaw using comprehensive coupled models that allow us to analyze in much greater detail the dynamics of these variations. Fortunately, the data doesn't stop, and the US colleagues have now access to an ice core through the West Antarctic Ice Sheet Project that gives us a glimpse of the last glacial with unprecedented resolution. As you see here in this figure that I took from Blizzard's paper in 2015, you see on the top the North Grip isotopic record with the time going from the left to the right. Then the methane that affords us the synchronization of the record in the south, and the temperature signal. Now, this pattern that you see here has been known for more than 10 years, but what these authors have analyzed, thanks to the very high resolution in their ice core, is a consistent lag of the temperature in Antarctica, both at the Donsker-Döschker warming as well as at the Donsker-Döschker cooling. And these authors argue that, therefore, this type of lag is independent of the state of the Atlantic meridional overturning. This is a very important result. It is a result that provides an essential test to the three-dimensional coupled climate models. But that's not the end of the story. That same ice core also provides us with information regarding the phasing of the hydrological cycle. As we know from the earlier studies, the hydrological cycle in particular in the atmosphere is important not only to determine the stability, potentially of the Atlantic meridional overturning circulation, but also causing collapses if this precipitation, if this freshwater flux changes substantially. So the question when and where this freshwater flux is changing during these abrupt events in the glacial is an essential one to understand the dynamics. You see here in this analysis, in red, again, the temperature proxy from the south, from Antarctica. Then in the middle, the temperature proxy of North Grip, which leads the temperature signal of the Antarctic, as we've seen before. And then the synchronization data, the methane data, and in blue, the hydrological information based on a modified deuterium excess formulation, which very clearly shows, both at the Donsker-Döschker warmings as well as at the coolings, that this is contemporaneous at the same time within the uncertainty of the northern temperature signal. This is really a great surprise. So in a way, the thermal response of Antarctica lags by 200 years, whereas the hydrological response is actually contemporaneous with the changes in the north. This is a second very important observation that affords a test of the climate models that we have available. Now, the argument, of course, is that the atmosphere plays a crucial role in transmitting the information from the northern hemisphere to the southern hemisphere. The authors here argue, and this is a paper that came out earlier this year by Markley, that it's the westerlies, both in the northern hemisphere and the southern hemisphere, linked to the ITZZ at the equatorial region, that causes the modification of sources of the hydrological cycle that can be traced then in the isotopic signal in Antarctica. Now I want to open up another window where data can give us extremely important constraints that are fairly independent from the constraints that we have discussed before. And that concerns the carbon cycle. You see here a classical picture from a paper by Bernhard Stauffer in 1998, who revisited the carbon dioxide variations during the Donsker-Döschker events that were thought for a long time to be of large amplitude. There was an earlier paper on Greenland ice where CO2 variations have been measured, but in this paper here we came to the conclusion that these variations are only on the order of 20 ppm during some of these variations of temperature during the last ice age. Of course, with the new ice that was available through the two projects of EPICA and Thales Dome, we could have a much higher resolution of ice on which we could measure the carbon dioxide concentrations, and a stacked record here, you could almost call that an ensemble analysis of Donsker-Döschker variations of carbon dioxide, shows that these amplitudes are on the order of 20 ppm, and that there is, for these events that I show here, a lag of carbon dioxide maximum with the warming, the abrupt warming that causes the Donsker-Döschker event. So you see here an emerging new constraint for coupled biogeochemical physical climate models regarding the carbon cycle and its temporal evolution during abrupt changes. Now here I show you the latest data that we have. It's still unpublished, but the fascination of these data is that we actually go back even further in time. We go back to the time of the marine isotope stage 9, 10, and 11. You see here in the red dots, I hope that is recognizable in the top curve here, you see the high-resolution carbon dioxide measurements that have been carried out by my PhD student Christoph Neerbas and are about to be defended actually next week, so we keep our fingers crossed, but the data that he's presenting here is just incredible. Look at the detail here of the carbon dioxide variations. You see essentially three features. You see, first of all, the long decline of carbon dioxide concentration into the glacial maximum superimposed by the so-called carbon dioxide maxima event, which go along with the Antarctic isotopic maxima, which you recognize in the lowermost curve that is given in black. Each of these variations in temperature is actually shown also and visible in the carbon dioxide concentration. The third feature, which was a surprise to us, is really connected with the steps that you see in this curve. You have to look a little bit more carefully. You see a step, for example, at 387,000 years before the present. You see another step which is remarkable at the end of MIS 9 and the beginning, at the beginning, of MIS 9, where you see an overshoot, a step, which I can highlight here, of the order of about 12 ppm at the beginning of an interglacial. We don't really know what the causes are of these steps that we see not only at the beginning of an interglacial, but occasionally also through the glacial. And in fact, we've seen these steps already long ago during the termination 1 in the first high-resolution CO2 record that was published many years back by Eric Monin. So this is another puzzle that I put before the modelers to try to come up with mechanisms that let us explain steps of about 10 to 15 ppm within about 100 years. That is about the maximum resolution that we can pull out of these ice cores at that age of the ice. We also show here a stacked record of the Donsker-Döschker event, of the Antarctic isotope maxima events and their CO2 variations during MIS 10. And you can see here a remarkable feature, again, which we cannot explain and that has to be taken as a challenge again for those who model or those who make hypotheses about the coupling of the physical climate system with the biogeochemistry. You see here the amplitude of these carbon dioxide maxima, with the largest amplitude in the top curve. That is the variation during the initiation of MIST 9, and then slowly going down to older variations of carbon dioxide. These amplitudes actually seem to decrease if you go further back in time during the marine isotope stage 10. Again, something that may or may not be a hard constraint on carbon dioxide models. Now, the final question that I have here in this ping pong, and we're now firmly arrived on the data or the paleoclimate data side, is where is the next frontier? I'm convinced that with this next frontier we will generate data, and by we I mean a big team of European colleagues. We will generate the data that provides the next hard constraints on climate models. What is this all about? I go back to the carbon dioxide record that we have extracted from the Epica Dome C ice core, and I compare it to the increase since 1958 of carbon dioxide in the atmosphere. You know, you're familiar about that increase. You're also familiar with this curve over the last 800,000 years, a variation that shows that our anthropogenic activity is far and beyond any of the natural variations of the past 800,000 years. Now, if we take that record and expand the timescale a little bit further, fortunately our colleagues from the marine sediment community can tell us something interesting about the earlier ice age variations. The ice age variations that so far we have not yet accessed with polar ice cores. You see here the stack published by Lisiecki and Remo here in the lower curve, and you can actually expand beyond the 100,000 year world, which is characterized by this typical timescale of the large amplitude ice ages, back in time to about 1.4 million years. Of course, Lisiecki and Remo go much further back, but I have stopped here at 1.4 million years ago. And the question is, well, what are the greenhouse gases doing? There is some proxy evidence, of course, about this 40,000 year world, that the range of carbon dioxide variations based on boron isotope reconstructions from marine sediments is about as indicated in this bar on the left side of the slide. But that doesn't really provide us with interesting information regarding the millennial scale variations that I think are important to extract information about the dynamics of the climate system. And therefore, I venture to say that the millennial scale greenhouse gas forcing is essentially unknown for a time that is remarkably different from the last 800,000 years for two reasons. First of all, the timing is about 2.5 times faster. You see here 40,000 year cycle. The 100,000 year signal seems not to be present. And also the amplitude of these cycles is much smaller. In other words, the ice sheets had a different dimension in this 40,000 year world. So the goal now is to look for this 1.4 million year old ice in Antarctica. And Hubertus Fischer and colleagues have come up with a set of criteria for this ice. The ice flow should be less than 2 meters per year. The depth or the thickness of the ice sheet should be less than 2 kilometers, and the basal temperature less than -5 degrees Celsius. You see here in this map areas regarding the estimates for the basal temperature. Everywhere where it's red, you should avoid looking for the oldest ice because that is a area where you are likely to get ice that is too warm. But you also see the large heterogeneity. For example, in Dome Argus, you have variations over short horizontal distances from relatively warm ice at the base to very cold ice at the base. So somehow we are still looking at this map only with one eye, and the other eye, the in situ information, is really missing. And that is why we've embarked at the University of Bern on a very specific project of a scale that we can still manage. Jakob Schwander from our institute has had a dream for many years to build the world's smallest rapid access drill. And that dream has been realized, not to completion, but very close in the last 5 years. It's a drill that should be able to drill into the ice to bedrock in about 5 days to a week with a minimum amount of logistic burden. You see here a sketch of that drill. It's a classical setup in the sense that you need a casing to get through the Föhn. It's a wet drilling, of course, because you go down to 2.5 kilometers or 2 kilometers in Antarctica, and therefore you need drilling fluid. This is a rendition, a graphical rendition of the design of this drill. It's a drill that has a very small dimension, a diameter of only 2.5 centimeters, so it's a Swiss miniature, if you wish. And with this drill that is propulsed by the drilling fluid itself, with this drill we like to access the deepest parts of the ice in order to get in situ information about the age of that ice. So the engine that drives this drill is in fact a pump. And this pump is used not to transport drilling liquid, but the drilling liquid is used to drive the pump. And you see, if you press the pump, if you press the drilling liquid through this pump that is enlarged there, the pump starts to rotate. The anchor of that pump starts to rotate and drives the drill head, which is shown here in this photograph. You see, this is a very sophisticated drill head with a screw in the front. It's actually self-propelling. It pulls itself down into the ice. You also see at the very tip of the drill 2 holes. Through these holes, the drilling liquid is exiting once you've pressed it through and is recycled upward through the borehole to the surface where the ice chips are separated from the drilling liquid. The first tests have been carried out at the EGRIP site in 2016. You see here Jakob on the right side with this very lean equipment, all built in the mechanical workshop at the University of Bern. You see the vertical black tube is the casing, and inside the casing you see a thinner tube. That's the tube that supplies the drilling liquid to drive the drill. Here are a few impressions of these tests. That's the last test this year in June 2017 at the same site, where essentially Jakob has drilled at a depth of 80 meters, that is at the Föhn ice boundary, 15 meters into the ice in 20 minutes. So I regard that as a proof of concept, and we're very much looking forward to the deployment next summer 2018, for the last test in Greenland before the equipment will be deployed in Antarctica. With that, I come to an end of my lecture. Let me summarize first the goals of the Oldest Ice project, the European project that is called actually Beyond Epica, Oldest Ice. We have identified a possible drilling site around Dome Concordia. That's certainly a site that we will first explore in the season now and next year. But the in situ proof of oldest ice will come only with rapid access drills. I've told you only about drilling a hole, but in this hole we will send down a sensor that allows us to measure the dust concentration, which is a good indicator for ice ages. We would like to cover a time of 1.5 million years, and with that, of course, we are very much looking forward to measure the greenhouse gases in the 40,000-year world. You see, this is still far away, but somehow you have to start with a dream. Let me come to the conclusion. We have seen centennial-scale climate reconstructions can offer a very detailed view of Donsker-Döschger events, Antarctic isotope maxima, and carbon dioxide maxima during glacial times. These are hard tests for the coupled physical biogeochemical climate models. The modeling of rapid change has matured, but I would argue that still important components are underrepresented in these models, and that is dynamical ice sheets, the isotopes both in the ocean and the atmosphere, and ocean tracers, which would allow us to forge a strong link with paleoceanography. Paleoclimate modeling, that is my personal opinion, must again become more predictive in order to avoid bias. It's one thing to simulate an existing paleoclimate record, but it's a completely other thing to make a prediction about the behavior of the climate system and then await eagerly the confirmation or rejection of your hypotheses through hard data. In stepping back a little bit, and obviously also with my experience of the past 7 years in IPCC, I would actually say that paleoclimate science must increase its visibility again under the current focus on anthropogenic climate change. You all know that there is no chapter on paleoclimate in the forthcoming 6th assessment report. That's a specific challenge. Some people say, well, finally our data has made it into observational chapters. Well, I still think it's a difficult situation where you compare apples with oranges and try to mix everything together. So we need to be aware of the visibility of our science in the light of ongoing discussions regarding anthropogenic climate change. And I think it's not that difficult because we have a unique selling point. The unique selling point is, in fact, we offer ensemble observations. Everybody is talking about ensemble climate models and model simulations. There is a huge effort on comparing different climate models, over 20 intercomparison projects with ensembles. But we do have ensembles in some sense in our paleoclimatic records. If you think about millennial changes over 1,000 years with decadal resolution, we have many of those if you go back 800,000 years or 1.4 million years, only that we have to work very hard on the forcing of the climate system. That needs to be quantified, and what I said about the Beyond Epica regarding the greenhouse gas forcing is just one step in that direction. With that, let me thank you, everybody, for coming here and listening to this lecture, but my sincere thanks go to all inspiring, challenging, and supporting science colleagues, friends, technicians, engineers, PhD students, postdocs, and everybody who has had a role in our so exciting science, which would not be possible without a little bit of money from funding agencies. So thank you very much, and I wish you good continuation of everybody's science. Thank you very much.
Is this on? Oh. Hello, can you hear me? We have time for quite a few questions, so if you have any questions, please come up to the microphones. Right here.
Right here. You can, or you can just take questions and you can have them.
I see Michael. But it's probably better if you speak in the microphone so everybody can hear you.
Thank you for an absolutely lovely lecture. I just wanted to mention that I didn't know that Geiss was your colleague, but I do know the paper, As a matter of fact, it is cited in my 1987 book, and it is cited in connection with the question, what was the trigger that took us from the 40,000-year world to the 100,000-year world in the context of what is called these days tipping points, and used to be called bifurcations at that time. And there was a little question about the nature of the bifurcations in Barry Saltzman models versus mine, and that's exact. So I hope we'll have a chance to talk about this afterward.
Absolutely. I think many of these ideas are buried in the literature, and you have to go back many decades, so that is much appreciated. But still, even in the old literature, we don't really know the millennial scale variations of many of these proxies that we would like to measure on the ice, but also on the marine sediments.
Other questions? Thank you very much.